Okay guys, welcome to my channel. In this video we are going to continue with the science paper 1 2019 for internals. So if you are new to this channel, then you must watch the first part of the video by clicking on the link that is appearing here, or you must watch also the second part of the video containing section B by clicking this link which is appearing here. All right, so let's go ahead with the section. Section C, 20 marks. Answer any two questions from this section in the answer booklet provided. C1, a spring with its upper end fixed hangs vertically alongside a meter rule. The lower end of the spring gave the following readings in table C1.1 when various masses were hung from it. So we have masses in this row and reading in this row. Then we have applied force in this row. Then we have extension in this row. So we are told when there's no mass hung to the spring, the reading on the spring is 10.0, all right? Or rather, the spring on the meter rule is 10.0, all right? Then when a mass of 0.2 kilogram is hung to the spring, then the reading now goes to 12.0. And when a mass of 0.04 is hung to the spring, then the reading goes to 14.0. When a mass of 0.06 is hung to the spring, then the reading goes to 16.0. When a mass of 0.08 is hung to the spring, the reading goes to 17.0. And when a mass of 1.00 kilogram is hung to the spring, then the reading goes to 17.5 centimeters. Then this row they are saying applied force here, we are told it is 0. Then here it's blank. Then here we are told it's 1. Then extension here we are told it's 0. Here it is blank, and then here it is 7.5. A says state Hooke's law. Then B says copy and complete the table for the values of applied force N and extension cm or centimeter produced. Then C, draw a graph of applied force against extension on a graph paper. Then D, on the graph paper show the elastic limit. So let's start with A. A says state Hooke's law. So let's answer this question. So we are going to say Hooke's law states that the extension of an elastic object is directly proportional to the applied force provided the elastic limit is not exceeded. So this is what Hooke's law states. Hooke's law is saying the force applied when extending the spring is actually proportional to the extension itself that the spring will undergo, provided that the elastic limit or the extension limit of the spring is not exceeded. So what does it mean, not exceeded? It means that you don't stretch the spring beyond what it can withhold. If you stretch it beyond, whereby if you let it, now the spring cannot go back, then here Hooke's law does not hold. All right, so there we are not are going to say the extension of an elastic object is directly proportional to the applied force provided the elastic limit is not provided, because in that situation then you would have exceeded the elastic limit. All right, so let's go to B. What is B saying here? So B is saying copy and complete the table for the values of applied force N and extension centimeters produced. So here we are told we should copy this table here and complete it for the values of applied force. So we must complete it by putting the values of applied force here and the extension is the values for extension here where they have left the blank spaces. All right, so let's go and see how we should do it. All right, so here is the table which we have copied. So how are we going to fill in these black spaces which they have left? So what you should understand, guys, here is that here they want force. So for you to be able to find force here, you must actually convert these values for mass here from kilogram to Newton by actually multiplying them with 10, because this force now here will be just weight, which you are going to find by saying that weight here, you are going to say weight, which is still force, is equal to mass times the acceleration due to gravity. So this acceleration due to gravity here, it is 10. So what we are going to get here are actually the weight now, and weight is always in Newton. All right, so this is why they're saying the force here. So what we will do now here is multiply 0.02 by 10, which will give us 0.2. Then we'll also multiply 0.04 by 10, which will give us 0.4. Then we'll also multiply 0.06 by 10, which will give us 0.6. Then we'll multiply 0.08 by 10, which will give us 0.8. And definitely this value here, I don't know, it could be that it's fine here, because when we multiply this by 10, we cannot get 1 here. So it means here they made an error. When you check, the difference between consecutive values is actually 0.02. So when you look at 0.08 and 1, the difference actually is 1.02, I'm sure, if I'm not mistaken. So this one was supposed to be 0.01 to make it actually uniform with what they have been using this way. That could be the one which could have given this value. So there was an error here. All right, then how are we going to find extension? So extension here is how the spring is going to extend when these forces are applied to it. So we are told the reading here of the meter rule, which was put alongside the spring, showed that when there was no mass hung, the reading was actually 10.0. Now when this mass is hung to the spring, then we see that the extension moves from 10 to 12. So by how much did this spring extend? It is just by subtracting 12 minus 10, which will give us 2. All right, then when they had to put a 0.04 kg, then the extension moved from this 10 actually now to what? To 14.0. All right, to 14.0, because we must be always be subtracting. So we are going to say 14 minus 10, which will be 4. So continue 16 minus 10, which is 6. 17 minus 10, which is 7. Then also 17.5 minus 10, which is 7.5. So you see, our calculations were correct. We have proved, because when we say 17.5 minus 10, we will get this value which they had to fill in themselves. All right, so let's go to the next question. So next question, which is C here. So C says and draw a graph of applied force against extension on a graph paper. All right, so let's go and see how we can plot. So we use these values here, applied force against the extension. So we'll bring our graph like that. Then we must label the graph to know what we are going to plot on the graph. So we are going to plot force against the extension. All right, so we know the values that represents force are these values here, and the values that represents extension are these values here. So if we are saying force against the extension, that means that the force must be on the vertical axis or the y-axis, and then extension must be on the horizontal axis or the x-axis. So we are now going to label the axis accordingly. So here we'll put a force in Newton represented by F force, and N represents the units, and then here we'll put extension represented by E in units centimeters. All right, then what we will now follow is now making sure that we put values here that are going to accommodate the force here. So how do we do it? So we look at the values for the force given here, or that we have, from 0 to 1. So we are moving from 0 to 1. 1 is the highest. So meaning that even the values that we must label here, 1, they must be uniform. 2, they must be able to actually accommodate these values. What I mean by uniform is that the difference between two consecutive values must be always constant or the same throughout the numbers we put here. So meaning that if we are to put 0 here, then here what value are we going to put? We start with the x-axis here. So we have 0, 2, 4, 6, 7, 7.5. So our lowest value is 0 and our highest value is what? 7.5. So we must make sure that we put values along the x-axis that must be able to accommodate all these values. So meaning we can begin from 0 and end on 8 or 7.5 itself, and then these values must be uniform, and that means that the difference between two consecutive values on each values must be constant. So meaning if we are saying 0, we can say 1, 2, 3, 4, 5, 6, 7. All right, so these values here are uniform, and the difference between two consecutive values is always 1. So if you say 2 minus 1, 1, 3 minus 2, 1, 4 minus 3, 1, 5 minus 4, 1, 6 minus 5, 1, 7 minus 6, 1. So you see that the consecutive values are actually constant. So what we are now going to do here is also to make sure that the values here accommodate the values which are here. So we'll say this one will be 0.2, then this one will be 0.4, this one 0.6, 0.8, then we'll have 1.0. All right, so these values here are actually the same ones which are here. All right, so now we are going to plot this, comma this. So 0, 0 will be there. Then we'll plot 2, 0.2. So 2 is here, 0.2 is here. Then we'll plot also 4, 0.4. So 4 is here, 0.4 is here. Then we also plot 6, 0.6. So 6 is here, 0.6 is here. Then we'll also plot 7, 0.8 here. Then we'll also plot 7.5 must be here in the middle, 1 here. All right. Then what we are going to do is now to draw a graph that will pass through all the points. All right, like that. So the next thing now that we are going to do here is actually to go to the next question. All right, so let's go to the next question, which is D. What does D say? So D says on the graph, show the elastic limit. All right, so our elastic limit is actually this value here. And how do we notice the elastic limit? So the elastic limit is noticed when the graph now does not go straight. So from 0 to this point, the line is straight. Now from this point to this point, the line starts to bend. So at this point, the extension of the spring is not directly proportional to the force applied. So here the force applied now is causing more extension to this spring. So meaning the elastic limit is actually reached and it has been exceeded. So the elastic limit is here where the line is straight, meaning the force applied and extension they are directly proportional. All right. So now let's go to the next question. So the next question is C2. So C2 says two lamps S and T of resistance 200 ohms and 300 ohms respectively are connected in series with a 240 mains as shown in figure C2.1 below. So we have these two resistors S here, this resistor S with 200 ohms and resistor T with 300 ohms connected in series, meaning they are connected one after the other. Then these, after connected one after the other, they are also connected to the voltage supply of 240 volts, and that there's that symbol, meaning this is actually connected to the AC supply, the one they are calling mains. Then A says calculate one current at point V. So we need to calculate current at point V. Then 2, potential difference across lamp S. So we need to know potential difference across lamp S. Then B, draw a circuit diagram showing resistors S and T connected in parallel. Right, we must draw now another circuit showing these resistors connected in parallel. Then C, using the diagram in 2B, the diagram that will draw in 2B, we will now calculate the one current through the lamp S and lamp T. So here take note that these are lamps that are offering those types of resistance. Then 2, total resistance of the circuit. So that circuit will draw here will also calculate its total resistance. Then D, give 2 reasons why lamps are preferably connected in parallel in ohms. So here you must give 2 reasons why it is preferable to connect lamps in parallel in our homes than in series. So let's begin with A, where we are saying calculate the one current at point V. So let's go like this. So we'll say this is our question. Let us push it aside here where we are going to calculate current at point V. So we are going to introduce the formula that connects current, because in this diagram, as you can see, we have been given voltage, then a resistor, here there are 2. So what we should know now is to introduce the voltage current resistor relationship, which says voltage is equal to current times resistor. Now what we are asked to find is actually current. So make current the subject of the formula, and we have current is equal to voltage times resistors, which we are going to say is equal to, then what we are going to do is to get this voltage here, which is 240 divided by, now since these resistors are connected in series, so we are just going to add these resistors so to come up with our total resistor, which will be 200 plus 300, which will give us 500. Then we are going to say current is equal to 240 divided by 500. It will give us 0.45 amps as our current. So part 2 says calculate potential difference across lamp S. Now we need to calculate potential difference across lamp S. So for us to be able to calculate potential difference at lamp S, we must be able first to just understand that potential difference of lamp S and lamp T, they are different. So we are going to say 2, since we want potential difference, we'll put the formula potential difference, which is voltage, is equal to current times resistor. So we know current that is passing here. Current in series circuit is the same through all components that are connected in series. So these components here, they are connected in series. So the current that is at point V is the same current that passes S, passes T, and it goes back like that, rotating in the circular manner. So we'll get the same current, which is 0.48 calculated already. Then we'll use this resistor here. So we'll say voltage is equal to 0.48 times 200, which will give us 96 volts. All right, so let's go to the next question, which is B, right? So B says draw a circuit diagram showing resistors S and T connected in parallel. So these ones, which are lamps, now we'll draw them as resistors connected in parallel. So we'll draw them like this. So this is the source of power. All right, then we'll connect it, then draw here and draw another one. Then what we are going to do here to draw them in parallel, so put them in parallel, one resistor here, another one here. This one will call it S, another one will call it T. All right, so these have been connected in what? In parallel. So we'll call this one 200 ohms, this one 300 ohms, and put our voltage there. So we are done with the drawing. Then we are now going to go to this C, which says using the diagram in 2B, this diagram here, calculate the current through lamps S and lamp T. So what current will pass through lamp S and lamp T? So what you should understand here is that current actually is not now the same in components connected in parallel, because current, when it reaches a junction like this one, it actually divides. Some electric current flows in this resistor and some electric current in the T resistor, and they join here and come back that side. All right, so what now we are going to do is to calculate the current. So let's have space somewhere here. So now what we are going to do, we are going to say C. So let's bring the question here. All right, current passing through resistor S can be given by voltage divided by actually resistor S. All right, so current divided by resistor S will give us the current which is passing there. So we'll say is equal to 240 divided by 200, which will give us 1.2 amps. So that is the current which is going through resistor S. And then what we are going to do again here is to calculate current going through resistor what? Resistor T. So say current going through resistor T is equal to V over actually resistor T itself, which will be equal to voltage, which is 240 divided by resistor 300, which will give us 0.80 A. All right, so here it is quite simple because we only have two resistors here. So we just use the actual resistors given, and then the voltage, actual resistors divide into the voltage. So yeah, those are our answers. Then we'll go to another question, which is, so let's have some space here. So part 2 say total resistor of the circuit, which is 1 over R. This one is total resistor, is given by 1 over RS, this RS plus 1 over RT. So this is the formula. Then what we are going to say is that 1 over R is equal to, actually 1 over, we'll put 200. RS is 200 plus 1 over 300. Then what we are going to do is, let's move this one and let's draw a line here. Then let's answer it from here. So what we are going to say is 1 over R is equal to 1 over 200 plus 1 over 300. So here we'll look for a common denominator in which these 200 and 300 can go. So these are fractions. Now we'll add them mathematically. So 1 over R is equal to, the common denominator is 600. So 2 into 600, which will be 3. 3 times 1, 3 plus 3 into 600, which is 2. 2 times 1, which is 2. Then we are going to say 1 over 3 is equal to, add 3 plus 2, which will be equal to 5. So 300. Then here we'll have 5. So 605. Then we'll make this one the subject of the formula R by cross multiplication. So multiply R times 5, which will be R5 equals, then 1 times 600, which will be 600. Then we'll divide here by 5, here by 5. Then 5 into 5, 5 into 5 will remain with R. Then equals 5 into 600 will have 120 ohms. All right, so this is our answer. Then now we'll go to the last one. Give 2 reasons why lamps are preferably connected in parallel in homes. So one of the reasons is that, 1, to avoid the power cut to other lamps when one lamp stops working. Then 2, to allow bulbs receive the same voltage and light with the same brightness. All right, so let's go to the next question. So the next question, which is C3, says figure C3.1 below is a diagram showing a bowling ball as it rolls down an incline for 5.06 seconds before reaching the ground or the horizontal ground. So we are seeing this bowling ball which will roll on the incline, and we are told it will take actually 5 seconds the whole time before it actually reaches the horizontal ground. And then here we are told the changes in gravitational potential energy of the bowling ball as it rolls down to the horizontal ground are shown in table C3.2 below. So the change in this potential energy as it is rolling are here recorded. So at 0, when no time passes, it is at that point it has this potential energy. When 1 second passes, it will have 7.2 potential energy. When 2 seconds, it will have 2.54. When it is at 3 seconds, meaning as it is still dropping, it will have potential energy for 3.6. When it reaches 4 seconds, or when it consumes 4 seconds, it will have the potential energy of 1.8. When the time of 5 is reached, as it will be reaching the horizontal ground, it will have now 0 potential energy, or it will have no potential energy. Then they are saying, A, state the law of conservation of energy. Then B, using the values in table C3.2, draw a graph of potential energy against the time. So let's go to another question. Here C says, calculate the height G, calculate the height h of the inclined plane when the potential energy was 9 joules if the mass of the ball was 900 grams. Then D, using the graph, estimate the kinetic energy of the bowling ball at time 1, 2.5 seconds, 3, 4.0 seconds. All right. So let's try to answer this question by stating the conservation of energy. All right. So since the question says here, state the law of conservation of energy. So the law of conservation of energy states that energy cannot be created nor destroyed, but can be transformed from one form to another. So let's go to the next question. So the next question, which is B actually says, using the values in table C3.2, draw a graph of potential energy against time. So we'll draw, using these values here, we should draw a graph of potential energy against time. So we'll answer it this way. So we'll get our table of values, put it here, and then bring the graph here. Then make sure label it potential energy versus time, meaning our vertical axis will be potential energy in joules. Then our vertical axis will be potential energy in joules. Then our horizontal axis will be time in seconds. Then we must make sure that the values here that we put on our axis here, always, you know, the axis can start with 0 or some other values. But here, since we are beginning from 0 for time, meaning we'll begin from 0, and also for energy we'll have 0. So now what we are going to do here, it is to plot now the values, for example, on the vertical axis. So we should put values on the vertical axis that must ensure that they accommodate these values here, and they are starting from 0, so, and ending to 9. So what I did, I said this one will be 2, 4, 6, 8. So my graph was too small to make sure that it will reach to 9, so it ended to 8. So I had 2, 4, 6, 8. All right. So even when I will miss out 9 here, I think the idea is the same. If this was large, it can actually extend somewhere here. All right. Then also we should put values on the time axis or the x-axis to make sure that they accommodate. And this is simple. We'll just say if this is 0, 1, 2, 3, 4, 5. All right. So these will be accommodated accordingly. Then we'll begin plotting. So I'll not start plotting from here because I don't have the value of 9, but I'll begin plotting from 1, 7.5. So 1 is here, 7.5 must be somewhere here. So if this is 6 here, 7.5 must be in there. If this is 6, 7.5 must be in the middle, and 0.5 must be somewhere there. All right, I mean it too, 7.2 must be somewhere there. Then 2.54, so 2 is here, 4 is here. So if we say 4, 4.2, 4.4, 4.6, 4.8, 4.9, this is 5, then 5.4, 5.6. Now 5.4 must be this value here. All right. Then we plot 3.6. So 3.6. So 3.36. So 3 here, 0.36. So this is 2, 2.4, 0.5, 0.6, 0.7, 0.8, 3.2, 0.4, 0.6. So this is 2, 4, 6, 8, 3, 2, 4, 6. So 3.6 is here. Then we'll have 4.18. So 4 is here, 1.8 somewhere here. Then we'll have 5.0 somewhere here, and draw a line like that. So this was actually a straight line. All right. So let's go to the next question. So the next question, which is C, says calculate the height calculate the height h of the inclined plane when the potential energy was 9 joules if the mass of the ball was 900 grams. So here what we are going to do is actually to know that at that height, when the ball, because the diagram now is like this, it's like this. Sorry, I can't draw properly. So this is the height they are talking about, and they're saying when the ball was somewhere here, the energy, potential energy, was actually 9 joules. Then they're saying if the mass of this same ball is 900 grams, then they want us to find the height, this one. So it's so simple. So just say potential energy, we will use the formula for potential energy is equal to mass times acceleration due to gravity times height. So this is the height they want, so make height the subject of the formula. So we'll say we'll put here potential energy as 9, which is equal to, so we are going to replace mass here. We'll convert this mass 900 into 900 should be into kg instead of grams. So we'll divide by 1000 and it will be 0.9. So we'll say where there's m, we'll put 0.9 times this is always 10 times h, which we don't know. Then what we are going to do, we will say 9 is equal to multiply this times this times this, which will be 9h. Then we'll divide this side. Okay, it's as good as saying h is now going to be 1. So what I did actually here was actually first thing I said 9 this side is equal to 9h this side. So to remain with h, I said over 9, even here over 9. So this 9 and 9 will go, so have equals h here. Here we have 9 into 9, 1. So meters, because we are dealing in meters, so h then will be equal to 1 meters. That's how those values were found. All right, so this is our answer. Then this one they're saying D, using the graph, estimate the kinetic energy of the bowling ball at time A 2.5 seconds, then 4.0 seconds. So get the graph. All right, so we'll go and get the graph and make sure that we estimate the kinetic energy when time was at 2.5. So go to the graph and we'll go per 2.5, which is here. All right, so 2.5, all right, is here. So when it reaches the graph here from 2.5 to the graph, then we'll go to the potential energy and read the value here, which will be actually 4.2.6. all right, so say potential energy now minus this value here, which is 9, the whole energy which was 9 here, the whole energy, potential energy was 9 minus now, which will be 4.65 actually. Yeah, it is in the middle, 4.5, which will give us 4.5 joules still. Then we'll go to the next question per 4 seconds. So come per 4 seconds here, we'll draw a line from here to there. So this is actually 1.8. So say 9 minus 1.8, which will give us 7.2 as our kinetic energy, because as the boiling was falling, some of the energy was actually converted to kinetic energy. So at these times we have found that the energy was 4.5. At this time the energy was 7.5. All right, so let's see. We began with 2.5. Yeah, so the kinetic energy was actually increasing. Yeah, so it is making sense from 4.5 to 7.5. So yeah, all right, so we have come to the end of the lesson. Okay guys, if you enjoyed the lesson, please give it a like, and if you haven't yet subscribed to the channel, please consider subscribing so that you don't lose on the coming video. All right, so please guys, bye, and please peace.